Thank you again for visiting back my channel, Cody Brainy. Today, we will discuss about binary tree or binary search tree. Uh, tree is also another data structure where there is a specific way of storing data in its node. So, if you look at this diagram here, this is basically has a root node. Okay, the data stored in a root node is called a key. We have already seen in our doubly linked list or singly linked list where we often call the data part as data. So here we use key. So both are same. Okay, data and key we use interchangeably and both are same. So there is a root node, and under the root node you can see child nodes, right? So 3 and 8 are child nodes of root node, and 3 has two child nodes, which is 2 and 5. 2 and 5 are called siblings because they share, I mean, they are having the same parent, so obviously they will be siblings. And then if you look at the overall uh, tree, binary search tree or binary tree, it has only one root. Okay, only one root is possible for a for the entire tree. The traversal can start anywhere. I mean, we will discuss traversal, right? Traversal later, but just understand it has a single root. Then it is connected to the descendant nodes or the downwards nodes using connectors, which is called a edge. Okay, a tree has different edges to get through a specific path. So then a path is kind of sequence, a specific sequence of nodes along with the edges, starting from the root to the leaf node. So can you tell me one path? So you can say 632 is a path because it starts from the root node, it goes through 3 and finally reaches the leaf node. So this is a path, right? This is edge. Uh, this is kind of going through a specific sequence through the edge and finally reaches the leaf node. So this is a path. So there are different paths or combination of paths in a tree. You might have already heard about shortest distance algorithm where we will be finding the shortest distance uh, between the nodes. We will definitely see that specific algorithm later, but just remember path is kind of sequence of nodes along with the edges for starting from root to the leaf node. Then there is a parent node, right? So parent node, it's obvious, like you know about it now by now. What's a parent node? A parent node will be having child nodes. Okay, so if a node does not have any childs, and if it is a descendant node or if it is downward, then this can be indicated as a leaf node, right? So because it does not have any childs associated with that specific node, so this can be indicated by leaf node. Okay, so now if you look at the overall subtree, there can be possibilities of subtrees. If you look at overall tree, it's not subtree. My apologies for making mistakes in statements, so let me correct it. So if you look at the overall binary search tree, you can see the possibilities of forming different subtrees in this entire tree. So one of the subtree is 3 as the root node and 2 and 5 as the child node. This can be a subtree, right? I mean, so This is called subtree, or descendant nodes forming subtree. So you will be hearing this word descendants, subtree, whenever we discuss about tree. But now let us get into the real business. Okay, there are two or let me count. Okay, there are two important concepts we should understand when we discuss about tree. That is the level. Okay, level or depth. These two things are same. Don't ever confuse with level and depth. Okay, level and depth are same. So let us discuss what is level. If you look at level 0, that's the starting point. It's a not the starting point. That's the root node position, right? The level under level 0 or in the level 0, the root node happens here in level 0. So basically, I noted here level under the fact sheet. That's a generation of node. Okay, so level 0 has a specific generation of node, which is the root node, and there is only one node at that level, right? When level increases, when we go down the hierarchy, level is going to increase. So when level gets increased to level 1, then you see the generation of nodes is also simultaneously or parallelly getting increased. Or I can say, an increase in a level is directly proportional to the generation of node. So level 1 has the maximum possible node as 2, right? There are only 2 maximum possible nodes that a level 1 can have. Okay, now if you go to level 2, you can count how many maximum possible nodes can have in this level. So if you look at level 2, 2 5, and then if we could have child nodes under this specific node, then another 2 will come. That will attribute to total of 4 nodes under level 2. Then there is an equation to help us to determine the max possible number of nodes at a given level. That is 2 raised to L. Okay, so let us check the accuracy of this equation, 2 raised to L. So assume we are at the level 1. So the equation is 2 raised to L. The value of L here is 1, 2 raised to 1, which is equal to 2. The maximum number of nodes at this level is 2, which is correct, right? 3 is one of the node, 8 is the other node, which attributes to 2, the count of 2. Similarly, at the level 2, the equation maximum number of nodes are 2 raised to 2, which is 2 times 2, which is 4. So we can have maximum of 4 nodes at this level, 1, 2, and if it has child nodes in it, then that attributes 2 to it, which contributes to 4, overall 4 nodes, right? So this is the definition of level. So if somebody asks you what is depth, that is kind of same thing only. This is also the depth of the tree. Okay, now comes the another important critical point, which is the height. Normally our programmers, right? Normally programmers used to make mistake when they define the height and the level. We are all human beings. We will get confused sometimes. So this is a classical example where we can make a mistake. The possibility of mistakes is more when we try to explain the difference between level and the height. So always consider level as a generation of node, accumulation of node. Okay, it points to the accumulation of node. Okay, how many nodes are at a given level. But when it comes to the height, it is actually the longest path. Okay, it is actually the longest path starting from the root to the leaf. That is the height of the tree. So you cannot have two heights. So when we evaluate the height of a tree, we will look at the longest path starting from the root, starting from the seeds. We will look into the longest path from start node 6 to the end of the tree, or by looking into the leaf. From root to leaf, what will be the longest path? That will be the height of that tree. So if you look at here, I will tell my height of tree is, height of my binary search tree is 2, because it's the longest path. Or count the number of edges. I can tell path is kind of edge only, right? So when you say path, it's like 6 to 2. That's a path. 6, 3, and 3 and 2. How many edges we are having in that? 2 edges. That's the height of the tree. Okay? That's the height of the tree. 2. 2 is my height of the binary search tree. Okay, so now you can also determine the maximum number of nodes at a given height. So if you look at this equation here, maximum number of nodes at a given height is 2 raised to h minus 1. So let us see the longest path. The height is 2, right? From 6 to 2 to the leaf node. From the root node to the leaf node, my longest path is determined as 2. Now the max number of nodes possible in this height is 2 raised to 2 minus 1, right? 2 raised to h minus 1. H is 2 here. So 2 raised to 2 minus 1, which is 2 times 2 minus 1, 4 minus 1, 3. So there can be 3 nodes maximum possible in this height, which is true, right? So in this height, there are 3 maximum possible nodes. So even in this height, if you try to determine the height by going into this way, 6, 3, and 5, in that height also, the maximum number of possible nodes on that specific path or in that specific height will be 3. Am I right? 2 raised to h minus 1, which is 2 raised to 2 minus 1, which is 3. That's about the height, right? So now you got a clear picture of what is level and what is height. So you might have already got the differentiation between these two, levels and heights. So now let us go to the key. What is key? Key is nothing. Key is the data. So we used interchangeably key or data. Key holds the data part of the node. So when we discussed about linked list, we discussed about quite two or three parts: previous, next, and data. So here in tree, sometimes we refer data part as key. Key and data are same. So we are good on that. Okay. So I think we discussed about almost all the stuff. Child nodes we discussed, parent node, edge. Edge is connectors connecting between two nodes, and root we discussed about it. Levels we discussed. Now let us really get into. Sorry, let me zoom it. Let me really get into the important core concept, which is the binary search tree, right? So in binary search tree, assume you want to insert data here. Okay, you want to insert integer data type here. The ground rule is the node's left child, right? So if you look at here, the node's left child should be having a value less than the node's value, the current node's value. Okay, node's right side should be having a value greater than its current value. So that is the ground rule. So if you try to insert any integer type it will always compare here. It will start comparing here, a root. Okay, then it determines, okay, I want to save a 9 in this tree. So input comes here. It compares 6 is greater than 9 or not. 6 is not greater than 9, right? It is less than 9. So 9 will goes here, right? Because right holds the greater value. The right side holds the greater value. The left side will always go for the smaller values. Okay, so if a 9 comes, it compare against 6, then it will be pushed to the right side. So it comes here. Now it will compare against, now the current node is 8. Okay, now it will compare against 8. Compared to, when it compares to 8, 9 is greater than 8. So it will push to the right. So node will be created here in this portion. So 9 will be saved here. Similarly, when I try to create this tree, I try to push 3. So 3 comes here, current node is 6. It compares with 6, 3 is less than 6. It pushes to a left side, so 3 comes here. So 3 is created here. Now a 5 comes. 5 compared with 6, 5 is less, so it pushes to left. Then 5 is compared with 3, it's greater than 3, then it pushes to right side. So 5 is now placed here. When a 2 comes, it compares with 6, push to right, and again it compares with 3, it is push to left, it is compared with 3, and then it is again pushed to left. So this is the ground rule for the binary search tree. Okay, whenever an insertion happens, a node's left child must have a value less than its parent value, and a node's right child must have a value greater than its parent. So that's the ground rule. If we follow this ground rule, it is very easy to implement algorithm for binary search tree, and then obviously implementation as well. Okay, so always remember the ground rule. Ground rule will help us evolving the algorithm. Algorithm will help us implementing the real data structure in action, right? So that's it. So this is some interesting stuff that I noted down from the other resources. So this is like maximum possible number of nodes in a binary tree having height h. So they are telling if there are height h, assume there are height h, then they are telling the maximum number of nodes in a binary tree is, so basically 2 raised to 0 plus, this is in height 0, plus 2 raised to 1 plus 2 raised to 2, etc., etc. And finally it will derive into this specific equation, and as a sum of gp of n terms. So this is all basic math, so it will derive like this. So I just noted down for for a curiosity purpose. So right now you don't really need to worry about, unless you are doing any PhD or any research on data structure, then this should be useful. But let us go back. So hope I have covered everything, but don't forget the ground rule for a binary search tree. Right holds the greater value. Always remember, right is the greatest person or greatest guy or whatever it is. So right holds the greatest value, and the left holds the smallest value. Okay, so that's the ground rule. And now I think there is one more thing I should discuss before winding up this session, which is the traversal. So we actually went through some of the traverse techniques when we discussed about linked list and singly linked list and doubly linked list, right? So here the traversal, there are two types of traversal. Sorry, three types of traversal: pre-order, in-order, post-order. Pre-order, in-order, and post-order. Okay. So this is very important, because most of the in most of the interviews, they ask what is pre-order, what is in order, and what is post order in a binary search tree. Why this question is so important? Because we use a recursion technique for all these three traversal types. Recursion play with its great potential when we use this pre-order, in-order, and post-order traversal. Okay, so what is pre-order? So pre-order is it first. It's all depending upon the root node. Okay, so always uh, it is all the traversal is all based on the root node visit. Okay, so all these three things are derived based on that fact. So pre-order means you should first visit root. That is pre-order. You should first visit root, then go to the left, and then go to the right. So root, left, and right. So that is what pre-order. Pre means you should have done something before, right? You should do something before. That's pre-order. So you should be visiting root first, and then left, and then right. Okay, that is pre-order. Now in order. In order means it's like in order: left, root, and then right. So the traversal will go like that: left, root, and right. Okay. Now post order means root will be the last. Okay, last in the traversal. That is post order. It's all with respect to root. That's the hint I can give to you. So now you can say what is happening in post order traversal. So post order means root will be visited last. So left, right, and then root. That is post order traversal. Left, right, and then root. That is the post order traversal. Okay, so you got it. Now let us go back pre order traversal. Right, pre order means root. First root will be visited, right, and then left, and then right. Okay, so when we but assume it's not like we are not only traversing the first node, right? Starting from the root, we have to traverse everything under it. We have to scan every nodes in the tree. So we use recursion, and then we will call, in the case of pre-order, we will be calling recursively these three things. Okay, first is a root, call the root, then left, and then right. Okay, so then we will call this recursively. So it will be placed in the stack, and then during the reversal, when the code execution goes in reversal, the stack is like last in first out, right? So it will automatically give us all the values. Don't worry about that. We will be discussing the implementation in my next session. So we will see it in action in Java. So at that time we will be discussing about how we can create a binary search tree, how it's pushing the highest value to the right and pushing the lowest value to the left of the current node, and then how we can do these three types of traversal: in order, pre-order, and post-order traversal in binary tree. That's very important to understand. Thank you for watching this tutorial. Thank you for spending time with me, and feel free to ask any questions or send an email to codybrainy@gmail.com. I will be responding to your queries. Thank you. Bye.